Okay, welcome to SQVe Structural Summit, session number 88. And today we are going to talk about composite steel concrete structures. Okay. So at present we are live at YouTube, LinkedIn, as well as at Facebook. But relatively, in my opinion, the stream will be more smoother at YouTube. So let's say if you want to switch to the YouTube, I'll just place the link of YouTube channel. So this is the link of YouTube channel. You can just switch on the YouTube and you all will be able to interact with us through the live chat. So based on the registration form, of course, a few of the questions are selected, but please keep on sharing your comments, your suggestions, your feedback, or whatever queries you have related to the topic. Please feel free to mention into the chat box. Right? Okay. Yeah. Okay, and today we have Dr. Jawed Qureshi with us, and in fact, he's having PhD in steel concrete composite structures. Okay, so let us get started, and let's have a very interesting discussion on the composite structures. Okay.
Welcome to SQVe Structural Summit. We are very much thankful of you for participation in the live discussions. Please subscribe to our YouTube channel of SQVe Academy and press on the bell icon. You will receive notification for the future events when we go live. Also, kindly like and share the video with the engineers in your network so that more numbers of engineers may be benefited. We are planning to come up with more and more important and informative videos. To support the initiative, you may join our YouTube channel of SQVe Academy with nominal monthly subscription. In return, you will get access to member-only videos at YouTube and the other perks. The subscription can be cancelled at any time. Step-by-step approach to join the YouTube channel is mentioned on the screen. For any doubts, you may get in touch with us through email address. Thank you.
Hello. Yes, welcome, Dr. Jawed Qureshi, once again on this platform.
Thank you, Bhavin Shah. I'm
welcome.
absolutely delighted to be here yet once again. Last
Yeah.
time we really enjoyed our conversation, and our
Yeah.
audience, they absolutely enjoyed it as well.
Right.
And this time again, we look forward to having a very great conversation.
Sure, sure. So before we start, can we have your quick feedback about questions or queries or input which you have received from the
Yes.
participants? Yeah.
There were so many questions. There were 500 questions, and it was very difficult
Yes.
for me to choose those questions. And with these kind of live session, the difficulty is that if the answer to some question is the one-liner question, then audience
Yeah.
they would not like it. So
Yeah.
I carefully went through questions and selected few
Great.
questions, and I ended up. It's a technical topic, so in technical topic, it's very hard to keep audience engaged. But I've tried my best to have that engagement in today's discussion. So be prepared, have your pen and paper ready, and I will be asking you questions and I'll be interacting with you. And then some of the questions were about fiber reinforced polymer structures as well, which is one of my another research area. And
Okay.
you're giving me ideas on how to have new sessions, and some of them really very interesting and very thought-provoking as well. So that gave me fresh ideas for research and development, and that created those questions in my mind as well. So I think you really have brilliant audience, Bhavin. And
Yeah.
I must thank you a lot for giving me this opportunity to speak to your audience, and some of audience will be mine as well, but the percentage will be really very tiny. And I hope this time that you will pronounce name of my university, University of East London, properly, which is in
Yeah.
eastern side of London.
Correct. Yeah. Okay. Okay. Great. So So I think now already people have joined, so we can start the session. Yeah. So should we start taking up a few questions one by one?
Yes, I think so. But before we start, I would like our audience to write in comment that where are they from, where are they joining us from, so that I know that we have global audience
Yeah.
and I know that who I'm interacting with, and that will be really lovely. Good evening. Yes, it's good afternoon here, so good evening. Thank you, Mohammed Jinia. So I
Yeah.
would like you to write in comments, where are you joining us from? Is it from India? It's from UK, USA, Australia?
Yeah. Great. So before they write in the comment box, we can take
Yes.
this first question. Like, kindly brief what are the composite structures before we get into any discussion.
Yes. Let's talk about what does it mean by composite structures. As you can see in the name, that composite means that when you are combining two materials together, we call it as composite structure. Now that composite structure can be steel concrete composite structure, it can be fiber reinforced polymer composite structure, it can be steel with timber, it can be pretty much anything. As
Okay.
structural engineering is progressing, we are trying new possibilities. What is possible? How can we construct it? And more importantly, in this day and age of climate emergency, we are trying to make our structures sustainable so that our footprint as structural engineers is less. And in my view, structural engineers or civil engineers, they simplify lives. Without engineering, this world is not possible. But we haven't projected our image enough to outer world so that they engage with us. But sustainability is at the heart of what structural engineers do these days. And for dealing with climate emergency, we come up with efficient and smart solutions so that our structures are not only sustainable but fit for purpose and demountable as well, so that at the end of life, when we want to get away with the structures, then we can reuse them. So this is becoming quite a norm these days, that we make structures which we can demount at the end of their service lives. Just to give you an example, I'm sure a lot of you would have seen wind turbines. Wind turbine blades these days are being used as footbridges. So at the end of their service lives, still, and service life is not more than 20 years. At the end of their service lives, they are still usable. Now we have to find another use. And another use is that we use them in footbridges as beams in footbridges. And then we combine it with other materials, timber, floor, and etc., to make a bridge possibility. In my view, composite structures are future of construction and future of structural engineering.
Yeah, great. Okay, we can see audiences from all different parts of the world as well as from different parts of the India. And in fact,
Okay,
one comment has come that please make a course related to composite structures. Yeah.
absolutely. I think this topic is really very popular on my
Yeah.
YouTube channel. One of my most popular videos, which are very
Uh,
long as well. Normally, long videos, they don't get much popularity. So on a steel concrete composite beams, design of steel concrete composite beams,
uh,
those videos are really very popular. So I can see that there's a lot of interest. So yes,
yes.
definitely. I think I will probably use this summer to create a
Yeah.
course using different design codes:
Yes.
American, Indian, British.
Mm-hmm. Yeah. Okay. So should we take few questions like whatever we received from the registration form?
Oh, absolutely. Yes.
Okay, just let me set this right. Yeah, so the first question is what is steel concrete composite construction? Already you touched upon this point. And where and why do we use composite construction?
Excellent. I'm going to share my screen.
Yeah, please.
When we talk about composite structures, in our mind, we can say that there are two materials. Now, what is the difference between steel concrete composite and reinforced concrete structures? So, reinforced cement concrete in itself is a kind of composite structure, but why don't we call it as composite? Now, I will tell you why. So, let's move on. In the steel concrete composite structures, we have concrete and we have steel. But same is the case with reinforced concrete structures. Why don't we call reinforced concrete structure as composite structure? The reason is that because dominant material in reinforced concrete structures is concrete. We simply use steel bars where we need tensile strength, isn't it? So that's why we call it reinforced cement concrete. But in case of steel concrete composite structures, we have two materials. And here we are talking about structural steel. By structural steel, I mean I sections, tubular sections, and these are complete sections which are embedded with concrete. In that case, dominant material is steel. So when dominant material is steel, we call it as steel concrete composite structure. Now, why do we use steel concrete composite structures? And where do we use it? And when do we use it? First, why do we use it? The reason is that there is no such material that we can call as ideal material. Tell me one ideal material and I will tell you that it is absolute lie. There is no material in this world which is ideal. Like human beings, every material has got its limitations. What are limitations of concrete? Really pretty obvious. Concrete is strong in compression, but really very weak in tension. Tensile strength is almost probably 10% or less. And how about steel? Is steel an ideal material? The answer is steel isn't ideal material as well. Steel can corrode and steel can buckle as well because the sections are very thin. So when we use them, they can buckle. So all materials have some limitations, some shortcomings, some demerits. Now, what do we do in that case? We combine them to make those two materials strong so that they complement each other. And that's why we combine steel and concrete so that the limitation of both materials can be overcome. And that's why we use it in steel concrete composite structures. Now, the major areas where we use steel concrete composite structures is first of all steel building. And here I will be focusing mainly on steel buildings. And I will be talking about composite slabs and composite beams in this lecture. I will not cover composite columns. I will talk about it briefly, but not fully. In a steel building, as you can see in this picture, we have steel beams and we have this steel member. On top of that, we have this profile sheeting slab. Now here we don't have any other option. We cannot have a complete steel slab. It's going to be really expensive and it will increase a lot of loading as well. So we try to use materials really efficiently. We use this thin sheeting, which is really, really very thin. You can't imagine it's just 1 millimeter. So we use this 1 millimeter thin sheeting, and we nail this sheeting to top of the beam, and then we weld shear studs through the sheeting to the beam, and then we put mesh reinforcement, and then after that we pour concrete. Together it forms a composite system, and we call it as steel beam with composite slab using profile sheeting or metal decking or metal deck. And together it really forms a strong and efficient connection. Now, in this case, we don't have any other choice, although we have a choice of reinforced concrete slab, but I will come to that in a minute. And I will move to next possibility, which is steel concrete composite beam with pre-stressed precast hollow core slabs. Now, hollow core slabs are used where a lot of spanning capability is required, as much as 17 to 18 millimeter column free or beam free space. In that case, we use these hollow core slabs. We bring these hollow core slabs on top of the beam, and then the shear studs are pre-welded, and we have reinforcing bar in this gap, and then after that we have in situ concrete, and together it becomes a composite system. So there are three possibilities. One is steel concrete composite beam with metal decking slab having a profile sheeting. Second is steel concrete composite beam with precast pre-stressed hollow core slab. And there's a third possibility as well. The third possibility is steel beam with solid reinforced concrete slab. Now here you can see that we have a beam, and on top of beam we have ordinary reinforced concrete slab. But the difficulty with this slab is that we require a lot of foam work underneath, and due to speed of construction in steel structures, especially in Europe and Western countries, composite beams with profile sheeting or with hollow core slabs are really very common. And composite beams with reinforced concrete slabs are not common because they require foam work underneath. So these are three types of steel concrete composite beams. One is composite beam with profile sheeting, second is with hollow core slabs, and third is steel concrete composite beam with solid reinforced concrete slab, which we do not use in Europe. And I'm sure I'll ask you in a minute that if it is used in India or not. Now, this system is really very interesting. This is steel CLT hybrid construction. CLT means cross-laminated timber. In this structure, this is Edge building near London Bridge in London. It's a 27-story office building. Here in this zone, play zone, cross-laminated timber, a slab made up of cross-laminated timber is used on top of steel beams. This building is to be completed in 2026. And timber was used for future flexibility so that we can remove this. It's demountable and we can reuse these structures. Now, it is one of the key things that reuse of the structures, which will be the future of construction and structural engineering, that we will be reusing lots of material. There will be a lot of emphasis on this area. This has got barium rating of outstanding. Barium is and LEED, there are organizations in Europe which rate buildings as per their sustainability requirements, and this has got outstanding rating. By the way, this Edge building is different from Edge building in Amsterdam. In Amsterdam, we have Edge building as well in Netherlands, and that has got 98.9% barium rating, which is really highly sustainable. It's got its own electricity generation plants inside, and it is really sustainable building. This is the cross-laminated timber which is used over here, and steel beams, they are supporting this cross-laminated timber slab. And as you can see over here, that at each fourth floor we have some other composite section, and I will tell you what's the reason for that. Removable mechanical fixings were used in this structure so that we can use it in future. At every fourth level, precast hollow core slabs were used so that we can ensure 120-minute fire compartment. So after every fourth floor, we have precast hollow core units. You can see here that the color here is quite different than color of these 3 floors. And this is precast hollow core slab. The reason is that we want fire resistance. And then I will move to why do we use composite structures? What will happen if we don't use composite structures? And in my view, we get at least 25 to 30% saving in terms of material cost if we utilize composite action. Now, these are 3 examples: composite beam with 406 178 universal beam, and second is non-composite beams. Here we have 533 210 and 305 305. This is a column section. Now all these sections, they have same loading capacity, and construction height, you can see it's 560 over here, and in case of non-composite it's 710. And for universal beam, normally we don't use a universal column in as beams. Here you can see steel weight is 100%. Here it is 60% more in case of non-composite I section. In case of non-composite column section, you can see it is double. It means significant reduction in cost. Construction height. Now, construction height is really very important. Here you can see construction height is 127. It's 27% more in case of non-composite beam, and in case of universal column it is 93. It is important to note that stiffness is quite a lot as well. In case of non-composite, stiffness is 72, and in case of column it is just 46. Can I say that by using steel concrete composite structures, we are able to save materials because steel weight is less? We are able to have less construction height, and we are able to have stiffer section, which leads me to this idea that steel concrete composite structures, they are strong and they are stiff. Now, same is the situation with columns. But composite columns are not very common. In case of composite column, here you can see that the dimensions are 70 by 70. In case of reinforced concrete is 80 by 120. In case of a beam over here, it is 160 by 40, and here it is 160 by 120. So you can see that significant reduction in height. I'm not sure about the cost of these, and these type of sections are not very common as well. But steel concrete composite beams are really very common. Now this leads me to a question for you, which is, how many of you have worked on a composite construction project, and what is the most common composite slab in India? So type your questions in comments down below. And I'm going to stop sharing my screen, and I would like to see your comments. That was quite daunting. I was just talking to the screen, but hopefully people would have seen me. That's absolutely fine. I can't hear you, Bhavinsha.
Yeah, so the response have started coming now.
So composite deck slab is common.
Composite deck slab. Yeah. Steel beam with metal decking.
Metal decking. All right. Okay.
Deck slab.
Deck slab.
Then only deck sheeting slab.
Deck sheeting. Yeah. All right.
Yeah.
Okay.
Yeah, so
I have worked quite a lot on this.
Yeah.
I have worked quite a lot on this area. I did lots of testing. I will show you as well today.
Great. Concrete with metal bars.
Metal bars. All right. Metal what does it mean by metal bars?
I'm not sure. So Varun, could you please elaborate this? One more thing.
It's a new thing for me. I want to learn.
Yeah.
Using composite slab with metal decking. Yes.
Okay. And deck slab with steel beams.
All right.
Deck slab. Yes. Also composite column for an expansion project.
Expansion project. All right. Okay. Yes. Absolutely.
Deck sheet.
Deck sheet. Okay.
Okay. Atul Dubey is saying that we are only designing composite joist in deck slab and composite column.
Composite column as well. All right.
Deck RCC slab over steel plate girder in railways.
Is it on railways? Okay, that's interesting. I want to know more about it.
Yeah. Okay, Vasant is saying common practice in India is RC and PT slabs, but using composite slabs are less comparatively.
PT means pre-stressed.
Yeah, post-tension.
Post-tension, sorry. Post-tension. Superstructure, shear stress, yeah.
Steel bridge superstructure with deck sheet.
Steel bridges, I'm interested to know more about how it's used in bridges. For those of you who have commented that it's used in steel bridges, just give me some details. I think, can I write over here in comments or
okay, whatever you want to write, I'll put it from my side. So here we are still getting few more listeners.
Yeah,
we're still getting few more
listening from KSA steel beams. Okay, all right. GCC, it's quite common.
Okay.
Excellent.
Okay, my work has a lot of steel 2-story gantry structure to hold cooling units for data center. Sadly, no concrete apart from foundation. Okay. Okay, someone is saying, I'm now working in a project where composite steel beam with reinforcement concrete slab is being used.
So, Suman, if you have some pictures, then please send it to me on my LinkedIn. Okay.
Sure. Yeah.
Because I don't have any picture of reinforced concrete slab. So some students and engineers, they ask me where's the picture. So thanks a lot.
Deck slab for large span auditorium.
Large span as well. I would be interested in that as well.
And Prince Verma is saying that steel with concrete.
This is another of research area. I used to work at University of Leeds, and I have a PhD from there as well. So my supervisor there, he used to work quite a lot on steel tubular columns with concrete filled, and they've done huge research on that. Yeah.
Great.
What's the maximum steel beam is?
Okay, I think this is the last comment we have received.
Excellent. I think we will go to next question. So
next question. So how is the construction process different for each composite beam? with solid hollow core, profile sheeting, and slim deck slab.
Excellent, excellent. I think it has given me lots of buzz actually by these answers. Honestly,
Yeah.
I've learned
Okay.
quite a lot. Yeah. So thanks for that. Thanks for.
Yeah.
I
Okay.
will share my
Still.
screen.
Sure. Sure. Please.
Yes. So for showing the construction process, you can see my screen now.
Yes, your screen is visible. Please go ahead. Yeah.
Yes. For showing the construction process, I will play these two videos, which would make it really very obvious. I'm sure a lot of you would already know about it, but just as a refresher, I'm going to play these videos.
Composite floor slabs generally comprise profiled steel floor deck with in-situ concrete cast over the deck. The deck acts as permanent shuttering and spans in a direction transverse to the secondary beams. Primary and secondary beams in composite steel frames are rigidly connected to the floor slabs by shear studs, which are connected to the beams by through-deck welding techniques. This allows the floor slab and the beams beneath to act compositely. Beam depths are therefore less than in equivalent non-composite frames.
And I will play one for hollow core slabs as well.
For shorter spans, precast concrete floor slabs can be used with steel beams. These precast units may be supported on the top flange of universal beams or on the bottom flange of asymmetric slim floor beams, or ASBs. An ASB has a wider bottom flange, which enables precast units to be placed without clashing with the top flange.
Then first I will talk about the beams with profile sheeting slabs or metal decking slabs. First, we bring profile sheeting on site, and this is the first step. And then we lay these sheetings on top of the beams, and the way we connect it with the beams is that initially we nail these sheetings to the beam, but certainly nailing will not provide a shear connection. So this is the first step so that they are in place. Secondly, we weld these shear studs through the sheeting to the top flange of a steel beam. So here you can see this is round shear stud or shear connector. This is a weld collar, and we weld these shear studs through the sheeting to top of the beam, and then you can see we get this configuration. The next step is we lay mesh reinforcement on top of steel deck. Now, what is the purpose of this mesh reinforcement? The only purpose of this mesh reinforcement is that this is used for temperature and shrinkage cracks. It is not doing any other thing at all. It is not providing tension reinforcement to the concrete because it's not at the bottom. It is at top. The only purpose is that we want to avoid those shrinkage cracks. Once this is in place, then we have in situ concrete. We pour this concrete on top of this deck. Now here, concrete is being placed, and then at the same time, it is being leveled as well. And once you level concrete, after that, we compact this concrete using machine. And then finally, you will have this surface on top. You wouldn't even realize that underneath that you have metal decking. And then after it hardens, then it is ready to receive service loads. Now, what type of profile sheeting do we have? Mainly, we have two types. One is trapezoidal decking. You can see this is oriented perpendicular to the axis of the beam, which means that it is a secondary beam configuration. And in secondary beam configuration, it is almost compulsory to use shear studs. In primary beams, it is not necessary, but in secondary beams, it is essential that we use shear studs. Another one is re-entrant decking. Re-entrant decking, again, shape is different, but the only limitation is that this goes up to probably 50 millimeter deep decking, while this one trapezoidal, it starts with 60 and then it goes to 80, and in some countries they have 100 as well, and in the UK we have about 150 decking, which has been recently released. Not recently, I mean it's in last 10 years. So these are two types of deckings that we use. Re-entrant decking is termed as dovetail decking as well in some countries. Now, how about pre-stressed hollow core slabs? How do we put those slabs on? In this case, studs are already welded to top flange of the beam. And note one thing here, that there aren't any studs on this tubular section, which you can see over here, which means that in case of hollow core slabs, we just use main beams which are oriented in this direction, in the direction of shear studs, and transverse to the direction of this beam. So we call this beam as main beam, and we call this rectangular hollow section as a tie beam. So it is not necessary to connect slab with this beam. Now you would argue, then why do we use this beam? And the answer to that is that we use these beams for structural integrity, structural robustness, and to prevent disproportionate collapse as well, which is another topic which we can discuss at some other point. To provide that entire frame action in a structure, we use these tie beams. The only exception is that at the edge, it has to be composite, because we want to provide a frame action so that entire structure is connected together. But intermediate beams, they don't need to be connected, and we call this configuration is as main beam and tie beam configuration. And the configuration that we use in case of profile sheeting slabs, we call it as secondary beam and primary beam configuration. Now here we bring cast units on top of the beams. In this case, direction will be here. And once they are placed, we pass reinforcing bar in between these gaps, and then we pour in situ concrete on top of that. In that way, it ensures composite action. Now underneath, almost at the top. And this is some of the testing that one of my colleague, he did at University of Leeds when I was a PhD student. I was working on decking slabs, and he was working on hollow core slabs. And this was quite long testing. It was 20-meter beam, and they were testing behavior of composite joints. And again, you can see that it is quite large beam, which was being tested over there back in 2010. The type of precast slabs, we have mainly two types, where we have no structural topping. We have these sections which we put on top of the beam, and then we pass this transverse reinforcing bar about 20 millimeter, and then we pour concrete on top of that. Secondly, we have this configuration, everything is same, except that we have structural topping by having some reinforcement, mesh reinforcement, and on top of that we have this topping. But no structural topping is more common in the UK, and I guess it must be more common in other countries as well. Now I have a question for you. What is the most used composite system in your region? I think I got the answer, composite deck. If there is any other composite system in your region, then put it in comments.
Yes. Okay, good. Okay, the next question may be, what are the key advantages and limitations of each composite floor types in terms of span, depth, speed, and structural behavior?
Excellent. This is very interesting.
Hmm.
Let me move on.
Okay, there are a few responses, of course. Deck slab, then with metal decks and hollow core slabs. Yeah, only one-way design is possible. Two-way design is not possible for slabs.
It is not possible now.
Yeah, rib and block slab.
What is block slab?
Yeah, okay, he can mention in more detail what is block slab. One more response, to cover steel column with RCC jacket.
Okay, jacketing. All right. Excellent. Okay, I'm going to share my screen now.
Sure.
Now, we have different flooring system. For example, if we have timber flooring system on top of steel column, then it is spanning capability is from 2.5 to 4 meters. The depth is 150 to 300, and construction time is medium, I would say. Degree of lateral restraint is very poor. It means that it does not provide any diaphragm action. Diaphragm action means that it does not contribute to lateral load resisting system. And we use it in domestic areas. But nowadays, with this CLT, cross laminated timber, we use sometimes in multi-story buildings as well, as you saw earlier. This information is taken from Manual of Design of Steel Building to Eurocode 3 from IStructE, Institution of Structural Engineers. This was published in 2010. So some information can be a little bit dated as well. So I will tell you which one it is. In situ concrete means reinforced concrete. The spanning capability is as much as 6 meters in this case. And the depth is 150 to 250, medium. On the other hand, here, degree of lateral restraint is quite a lot. It's very good. And diaphragm action is very good as well. And we can use it in any type of structures. Precast construction, this information is dated. This is in this book, 3 to 6 meters. But nowadays, we have precast hollow core slabs, which can span up to 18 meter. And I will show you some of load span tables as well. And nowadays, typical depth can go up to maybe 450 millimeter as well. And we use it in a system where we have column-free space required and we have beam-free space. In some of the classrooms at University of East London, we have this precast hollow core slab being used. By the way, University of East London is entirely made up of steel structure, steel and concrete composites. And construction time here is fast because we don't need any form work. Degree of lateral restraint is not that much in this system. And we can use it for pretty much everything, all types of buildings. Profile decking slabs. Shallow decks, they can range from 2.5 to 3.6. Deep decks, they can range from 4.6 to 5 meters. But nowadays, they can span up to 6 meters as well. And nowadays, we have slim deck slabs as well, which can span up to maybe 8 or 9 meters as well. And 110 to 150 and 200 plus, the construction time is fast and degree of lateral restraint is very good. And diaphragm action is very good as well. And we use it in almost all categories, but the vibrations must be checked. Now I will move to what is spanning capability of different sheetings. And this is very interesting. 50 millimeter spanning capability is about 2.5. So if you have 2.5 slab span, remember that this is span of slab. Then use this. 60 millimeter, about 3 meters. 80 millimeter is about 4 meters. And 146 MD king span, multi-decking span, it can span up to 5 to 6 meters. So this is very deep sheeting. Remember that all design codes, American, Canadian, Australian, British, Euro codes, they are all based on testing for sheetings which were from 50 to 80 millimeter deep deckings. So anything after 80 millimeter, 100 or 120 or 150, we don't have any formula for shear studs. And manufacturers, normally they will provide that formula, which means that more and more research is required to bring these things in different design codes. We cannot simply rely on manufacturers' guidelines. That is just, they will just give you empirical value. They will carry out testing and then give you empirical value. So a lot of testing is required, in my view, to bring them into design codes. And if you work out shear stud connection for strength of shear stud using this decking, using Eurocode formula, you will get wrong results. That will not be realistic. So this is a knowledge gap that needs to be filled. And ASB is the slim floor deck, where you can see that the decking is inside the bottom flange of the beam. It is 6 meter plus. What is asymmetric slim deck beam? Here, the decking, it rests on bottom flange, and then we pour concrete and then we do everything else. The purpose of this type of system is to reduce the depth of the section. And here the depth is 255 to 400 millimeter overall, and it can span up to 6.5 for unpropped construction and up to as much as 9 meter for propped construction. Now, what is ASB? I will play this video here.
SLIMDECK is a proprietary shallow floor system. It is a composite system comprising of an asymmetric slim floor beam, or ASB section, contained within the depth of the slab. The ASB supports deep deck profiled metal decking. SLIMDECK reduces the construction depth, since the beams are contained within the depth of the floor slab. This reduces the overall depth of the floor structure and gives 60-minute inherent fire protection. Spans of up to 9 meters are possible, and service ducts of up to 160 millimeters diameter can be accommodated within the trough of the decking. SLIMDECK.
So now I would invite you to have any comment. And my question to you is that which type of composite beam would you not consider as laterally restrained? Please type in your answers in comments and I'll get back here.
Yeah. So meanwhile, a couple of responses we have got for the previous question. Okay, here in
Colombia. All right.
Colombia, composite beam with sheeting is used. Yeah. And
Trinidad and
in
Tobago. All
Trinidad
right.
and Tobago, yeah, blocks and precast beams are also used, similar to the UK.
Okay. So somebody is joining us from Trinidad and Tobago. All right. Excellent.
Yeah.
So we have global audience.
Yeah. Both metal decks and hollow core slabs are being constructed. Okay, one question like, is the spanning not dependent on thickness and profile?
It depends on the thickness of the deck. It depends on the profile type as well. So as I mentioned, that 50 millimeter will not have much spanning capability, only 2.5. On the other hand, 146 millimeter will have a lot of, in my view, load span table, they would give a lot of depth of concrete. I would not use a lot of deep concrete. So for example, for 60 millimeter deck, I would use the minimum one, which is 130 millimeter overall depth. And if you increase depth, obviously in load span tables, you will have a lot of depth as well, but that increases a lot of dead load on the structure. Unless if you have any concern about vibrations and stuff, don't use very deep decking. Use deep decking, but don't use depth of concrete, which is quite a lot. It is dependent on thickness, yes. So thickness, most of these sheetings, they start with 0.91 millimeter, 1.2 millimeter. So as you increase thickness of the sheeting, the spanning capability increases as well. Yes, I was giving this rough idea. I will give detailed load span table little later.
Yeah. Many times it's also used in retrofitting projects.
Retrofitting as well. All right. Excellent.
Yeah. Okay. Steel beams without shear connector will be laterally unrestrained.
Steel beam without shear connectors will be laterally unrestrained. Yeah.
So as you
It is
rightly said,
quite
there is always a question.
Yeah.
Yeah.
Steel beam without.
Yeah. So whether span depth ratio of IS 456 are applicable in precast members also? Okay, that's a different question.
I will have to double check because.
Yeah, so these ratios are for the conventional RCC structures, whatever
Okay, all
details
right.
which are. So
Okay.
whether those span depth ratio given for the conventional structure, is it applicable? Same is applicable to the precast members?
No, not at all. No. They're different. Let's move to the next question.
Yeah, sure. I think that's better. Yeah, very interesting question. Right? Is it possible to size composite slabs without detailed structural calculations?
That's a very interesting question. And the quick answer is yes.
Okay.
That is what most designers do. The quick answer is yes, it's possible to select a profile sheeting based on load span ratios without detailed calculations. And here are some manufacturers in the UK, Tata Steel. I'm sure it will be in India as well. Tata Steel is Indian. Kingspan, Richard Lee's, Structural Metal Decks, SMD, and CMF. These are few manufacturers, and I will go through their load span tables, and I will tell you how to size the slab as well. Load span table for 50 millimeter deep re-entrant or dovetailed deck. This is ComFloor. It's been taken from Tata Steel. So here, what you do is that you have applied loading. This is service loading, unfactored service loading. So for example, if you have 5 kilonewton per meter square service load, and if you wanted 60 millimeter of fire resistance for 90 and 120 minutes, you will have separate load span table. Now here you can see that the spanning capability is 2.79 meter, and mesh that you're going to use is 142. 142 means I think it would be probably 6 or 7 millimeter center to center. Search it up. I'm not exactly sure about the diameter. And this is the thickness of the sheeting, 0.9. And as you can see that when we increase thickness, the spanning capability is increasing. So for 1.2, spanning capability now is 3.37 as compared to 2.79. But again, it's not huge increase in spanning capability. But as you increase the depth of concrete, overall depth of the slab, you can see that spanning capability is reducing. If I'm the designer, I would always use the first possible. I will simply use 110 rather than 200 because it is reducing spanning capability first, and secondly, it is increasing dead load quite a lot. Unless if you have particular requirements for vibration of these floors, which should be checked, unless if you have those requirements, by all means, go with a simple one. Go with the smallest one. So in that way, you can justify that using this sheeting, using this height of the slab, and using this mesh reinforcement, you can use this sheeting without performing detailed calculations. And for ComFlow 60, again, you can see for 5 kilonewton per meter square, we have a spanning capability of 3.5. And again, as you increase loading, spanning capability is decreasing. So this is giving you idea which sheeting to use. But again, these tables, they come from manufacturer, and I'm sure in India you will have similar sheeting load span tables. And for 80 millimeter, you would see that we have more spanning capability. We have 3.7. For 50, initially it was 2.79, so increase of 1 meter. And again, if you're using thicker sheeting, then it will have more spanning capability. Now, how about this trapezoidal deck 146 mm deep from Kingspan? Here, see that for 1.2 millimeter, they come into two sizes, 1.2 and 1.5. And this is the sheeting which I tested myself as well. I will show you in a minute. Here, spanning capability is as much as 5.74. And as you increase loading, the spanning capability is reducing, but not much. So 5.74, 5.33. So it is giving you an idea of how to size these slabs without performing detailed calculations. And again, this is the load span table for asymmetric slim floor beams. This is ComFlow 225, and here you can see spanning capability is quite a lot, 6 meters. But for this slab, you would need bottom flange of the beam, which is wider than top flange. Now, hollow core spanning capability for normal hollow core slabs, 150 to 250 millimeter, we use these hollows you can see over here. And for deep decks, 300 to 450, you can see that shape of these hollow portions, it is different. Now, first is slab with structural topping. Here on right side, you can see a service imposed load. This is unfactored one. And for 5 kilonewton per meter, you can see that if you're using very deep deck, it is 14, as much as 15 meter as well. So we are pushing boundaries in terms of structural engineering. We are having more and more column free spaces with these kind of sheetings. How about with no structural topping, which is more common? Here again, see that spanning capability is quite a lot. If the loading is less, then you can see it can span up to 18 meters. So from here you can get idea that even without performing detailed calculations, you can still size the slab based on load span table from manufacturer. My question is that, have you ever used manufacturers' load span tables, or do you normally use rule of thumb methods for slab design in practice, especially in steel concrete composite structures? So type in your comments in the comment section below.
Okay, one question, like, are these span based on deflection limitations? So deflection limitation is considered. I think that's the question.
I'm not sure how they developed these, but I'm sure they would have considered deflection limits. Yes.
Okay, Ajay Kaushal is saying, cannot we use plates for flooring and decking systems?
Okay, that's interesting.
If the slab spanning increases as the depth of the slab increase, the strength of the slab would be weaker.
If the slab depth increases,
Okay, next comment. Yes, I have used the tables. I had to check the shear studs, however.
okay, excellent.
So
The
I
shear
think, as you
studs will
said,
be
that is always
completely clean.
shear
Yeah.
stud is always one of the gray area. Yes. Okay. Manufacturer recommendations are used. Okay.
What
Okay.
manufacturers are there in India and in Middle East? Who manufactures these sheetings?
Yeah. Okay. So I think someone may put some references, whichever references they are using. Right?
Okay, all right. Just put.
So is yeah. Okay, Rutvik is saying that, are there any specific deflection criteria, same as conventional slab as per codes? Also, please share which country code referred for the design of composite structures. Okay. Kishore Gawali is saying that load span tables are used. Okay. Manufacturers tables are used.
Tata Steel, all right.
Yes, Tata Steel, yes. Okay. Nilesh Parekh is saying that we can't use
We can't
plates.
use plate. All right. Let's move to the next question.
Yeah. How are the composite beams supported and framed structurally?
All right, that's an interesting question.
Okay. Meanwhile, a couple of more input, like one is JSW.
Okay.
And, okay, load span table given by the manufacturer. Okay. And Kishore
Okay.
is saying that usually the hollow core slabs bend upwards due to action of pre-stressing. How this is addressed when slabs are to be fixed inside I-beams?
Okay, I think there's always some kind of pre-cambering done in these kind of slabs. So when you apply service loads, they will adjust, in my view. And that pre-cambering will not be that large, so that it will not allow fixing.
Okay. 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 Tata Blue Scope is one more answer.
Okay. So should I go with the answer to this question?
Sure, sure.
Okay.
Please.
So we use two configurations. One is primary and secondary beam configuration for composite beams with profile sheeting. And typical floor grids are 7.5 by 12 or 6 by 9. And I mean, here it is not sure, it is 9 by 9 grid, but it's not very common. Secondary beams are most of the time twice as long as primary beams. So whenever you're using this configuration, try to use longer secondary beams, and primary beams should be smaller. Now here, the way load transfer happens is that load is transferred from slab to this composite secondary beam, and from this composite secondary beam, load is transferred on this primary beam, which is in vertical direction, and there are 3-point loads over here. For secondary beams, sheeting is perpendicular to the axis of the beam, and for primary beam, sheeting is parallel to the axis of the beam. For secondary beams, 100% you need shear studs. Without shear studs, you can't construct them. Whether you consider this as steel concrete composite beam or restrained beam, it is up to you. If you consider it as a steel concrete composite beam, then you will be saving 25 to 30% of depth of the section. But if you design it as restrained beam, then the depth will be 30% more. But normally in industry, we design them as steel concrete composite beams. But for these primary beams, it is not necessary that you provide shear studs. And the composite action is not necessary. If you provide it, it's fine. If you don't provide it, it's all right as well. The only exception is edge beam. So if the beam is edge beam and it is primary beam, then almost certainly you need shear studs over there. This is one configuration. Another configuration is composite beams with precast hollow core slabs. In this case, see that this is the span direction of the slab, and these beams which are in horizontal direction, these are, you design them as secondary beams, and these are considered as main beams. But the one that you see over here, the dotted ones are tied beam. You don't need any shear studs there. They are not taking any load. They just take self-weight of the structure, or you can probably add 10% of the load for the entire grid. But they are not taking any load, so they don't have to be composite. The edge beams, on the other hand, you need to make them composite for frame action so that the entire structure is tied together. So these are two configurations that we use in steel buildings. So at this point, I would like to move to next question. I can't hear you, Bhavin.
Yeah. So if we can take this one question before moving to the next point. Right. Does the topping of deck slab of maximum 7 centimeter, is it enough to consider it as a rigid diaphragm? That is enough to transfer the lateral load to the horizontal resisting system in the direction opposite to the sheet span direction. So this topping usually reinforced with a light mesh.
Yeah, topping on top of, are you talking about deck slab? Yeah, deck slab.
Yeah, on deck slab, yeah.
I'm not sure if you consider it as rigid diaphragm, probably consider it semi-rigid diaphragm or something. And normally this can provide lateral resisting system, yes. But the hollow core one, it does not provide. But how much is sufficient? Again, refer to design codes. Different design codes will have different configurations.
Yes. Okay, next question is, what are the key advantages of using composite slabs?
Okay. My screen is not shared, isn't it?
Yeah, yeah. You can share it, please.
Yes. You can see my screen now?
Yeah, please.
So what are key advantages of composite slabs? This is really very important, and I get asked this question quite a lot as well. First thing is that these are very fast. And the main reason is that they don't require any formwork underneath. Although in some cases, you can use props underneath to increase the spanning capability of these slabs, but they don't require any formwork, which saves a lot of labor, and also it saves cost as well, because labor cost is quite a lot, especially in Western Europe. And secondly, installation is easy. And these systems are building services friendly. So you can pass services quite easily. As you can see over here, that services are being passed in this ASB slim deck beam. And thirdly, slab openings for building services can be formed easily as well. Again, there are different requirements in different countries. How do we have these slab openings? In the UK, we have a Steel Construction Institute, and they have these guidelines. Now, one of the key advantage of using profile decking is that it can be used as temporary formwork during construction stage. It can support all construction loads. It can stabilize supporting beams against lateral buckling as well. So, and it can act as permanent working formwork for construction activities. So people can walk over steel sheeting. And it can provide protection to workers as well. Now, first, it acts as temporary formwork during construction, and then it acts as permanent formwork during composite action. Now, at composite action, it is ready to receive all service loads. The key thing to take away here is that it acts as tensile reinforcement to concrete slab, and in that way, it forms a composite structure. So there are two purposes. It is formwork where it is being constructed. So once concrete is hardened, it acts as tension reinforcement. If we didn't have a steel deck, then imagine what will happen. The slab is going to fail miserably, and it gives a shape to concrete as well, because concrete can be molded into anything. And the beauty is that nowadays you can use these demountable shear studs, which can be bolted to the flange of the beam. And as a result, you can remove these slabs anytime you want. So the shear studs don't have to be welded, but still we need a little bit of more information about it. Research is undergoing, and they are not still included in design codes. Okay, can we move to next question?
Yeah. What are the key components of shear connection in the composite slab.
Excellent. This is one of my favorite topic, and I did a lot of testing during my PhD as well on this topic. So I will love that topic. Let's. So what are the key components of shear connection in composite slabs? Now, this is shear connection in slabs, not in beams. In beams, we talk about most of the time shear studs. But here, we have frictional interlock. Due to shape of this deck, you can see that it is preventing this deck from moving upwards. This is reentrant profile, and this is some kind of profile as well. And again, if you have trapezoidal profile, that will prevent the deck from moving upwards. And then we have mechanical anchorage. Here you can see we have some indentations in the slab. These indentations, they will prevent the slab from moving in longitudinal direction. And longitudinal shear is one of the most important topic in this area. And thirdly, end anchorage. Here we provide shear studs at the end, and they ensure that the concrete is not moving in any direction. And sometimes we have end anchorage by deformation as well. So here you can see we have this deformation in the sheeting that prevents the sheeting from moving anywhere. So this is how we provide shear connection in slab. Now, typical configurations of these slabs are materials. They are 0.75 to 1.2 millimeter thick. Now, this information is again a little bit old. These days, we can have 1.5 millimeter thick sheetings as well. And in Australia, they are producing sheetings which are really very high strength, up to maybe 700 Newton per millimeter square. And sheeting thickness can be 0.9. So we are pushing boundaries as structural engineers. Cross sections, height of the stud 38 to 75. Again, nowadays we have up to 150 millimeter deep decks as well. And B naught is the width, so width up to 300 millimeter. Spanning capability 2.7 to 4.5, but these days we have up to 6 meters as well, as we're getting new and new products each day. The key thing to note here is that I think one of the questions was that how do we find out the properties of these sheetings? Most of these modern profile sheetings, they are slender sections. So calculation of bending resistance is really very complicated, and it will involve lots of testing before we can depend on it. So mostly bending resistance of these sheetings, it depends on experimental testing, and manufacturers most of the time they would provide the bending resistance of these sheetings. Now, why bending resistance of sheeting is important? Why do we need it? What's the purpose? In my opinion, we need it because we want to ensure that when we are putting concrete on top of sheeting, it does not bend excessively. And when workmen, they are on top of steel decking, it does not bend. So we need to have that bending check. So then I will move to the next question. Thanks, Bhavin.
Yeah, sure. Most welcome. Yeah, the next question which we can take up, I think. How do we find properties like moment of inertia and area of profile still sheeting, right? Are we expected to calculate them manually?
That's very interesting. Again, Let me share my screen.
Sure.
Most of these properties, they are provided in manufacturer guidelines. And the reason is that these sheetings, they undergo a lot of deformation and they undergo buckling as well. So we don't know how to work them out, but I have a sample calculation to find out effective properties of sheeting. But most designers, they will do these calculations. Most designers, they will depend on manufacturers' guidelines. And how do we work out bending capacity? And this is the testing which I did. I was involved at University of Leeds back in 2010. This is Kingspan multi-deck 146 millimeter decking, and it is 5 meter long. So we applied this loading on a sheeting, and we saw at what load it fails, and it became a commercial product in 2012. And this was proprietary decking, so it was not a commercial product back in 2010. And this was a test setup. So we applied this loading, this 5 meter in this direction. University of Leeds, where I did my PhD from, they had giant facilities, so we were able to test lots of things. And after failure, you can see that deck is buckling over here. You can see slight depressions, and you can see these embossments which are running in this direction from left to right. Surprisingly, when you see it, I think most of you would have seen it, if you see it on other side of the deck, they will run from right to left. So which in itself, it provides a resistance. It means that it is resisting it from moving in longitudinal direction. So it is providing longitudinal shear resistance to concrete, because the direction of these embossments, it is reversed on other side of the deck. So it is left to right on the visible side. The side which is not visible, this web which is not visible, it is from right to left. And then I did some, this is another view of the failure. I did some numerical modeling as well, which was fairly close. And from there, we got and from this testing, we got this value, 32.4. In my testing, we tested 4 specimens, and on top of my head, I just saw my documents yesterday. I saw that I worked it out as 32.8 something. So it is reduced slightly, 32.4. So that's how we determine the value, ultimate moment resistance, using testing. And most of manufacturers, they get this testing done and then they write this over here. Now, how about if we don't have access to testing? How about if manufacturer does not give us this value? Remember that the main purpose of this ultimate bending capacity of sheeting only is that we want to ensure that wet concrete is supported properly without bending, and workmen, they are supported as well, they don't fall down. But how can we manually determine elastic properties of class 4 or slender sections when experimental bending moment is not available? And the key lies in going to basics. In my view, basics are really very important. So this is from plate bending formula, be effective. And this formula does not belong to any design code. It is a universal formula that's been developed. So we can find out be effective using this formula. And I have a worked example, but I will not go through worked example. You will have copy of slides. Bhavin will let you have the slides. Now I will quickly go through. This is the example where we have the sheeting, and we will work out B effective, and from there we will work out moment of inertia, and we will work out all other details. So first we work out B effective. Once B effective is worked out, then we work out elastic neutral axis using first principles, and from there we get this Y value. And once we have this value, then you work out second moment of area, or in India I think they call it as moment of inertia. T is too small, and I think we ignore T, and then after that we work out contribution from top flange, bottom flange, and web, and then we have this value, and we divide it with 300 millimeter width was 300 over here, and from here we work out moment of inertia per meter run. So that's what you will find in many manufacturers as well. So many manufacturers will give you this value, and from here we work out W elastic section modulus. Once we have elastic section modulus, then moment elastic will be elastic section modulus divided by Fy, and from here we get 6.3 kilonewton per meter. So that's how we work out the moment capacity. You will have copy of these slides, and then you can go through this example yourself. I'm doing it quickly in the interest of time. Then I will move to next question.
Sure. The next question could be, what are the typical failure modes in composite slabs with metal decking, and why is the MK testing is important for the composite deck profiles?
Yes. Thank you. Thanks for this question.
Yeah.
And again, I did this testing as well at University of Leeds, and when I was a PhD student there.
Okay, great.
So why MK test is important? First, if I zoom out from my understanding as a structural designer, then I will think about possible failure modes. So when I'm designing anything, I normally think about what are the failure modes, and to account for those failure modes, we do some calculations, and then we design a system. So in case of simply supported composite slabs, there are three possible failure modes. One is flexural failure, which happens at this one section, and one section is over here. And second is failure in vertical shear, which happens at this point, 2 near supports. Now, these are typical failures in any beam type structure as well. What is different from beam type structure here is third one, which is failure in longitudinal shear. In this case, the failure will happen in shear span over here, which is a quarter span from supports. Now here we want to avoid this shear bond failure. And the way we find out if structure is fine in shear bond as well, we carry out this MK testing. And we find out these parameters, and manufacturers will include these parameters. But as this process is very empirical, it's experimental, and major design codes, I can say for sure that Eurocode, they are considering removing this method for the next generation of Eurocodes, which will be released in 2026 to 2028. So first, flexural failure. For flexural failure, again, we work out the moment capacity using these formula. I will not go into details of these formula, and you will have copy of slides. And secondly, we have shear in vertical direction, for which we have again this formula, and we work out vertical shear. And the important bit here is longitudinal shear resistance to account for shear bond failure. Now for this we carry out MK test, and we carry out testing on two specimens, 5 meter and 3 meters. This is 5 meter slab on Kingspan 146, and 3 spans were tested here. And at this point where load is applied, we have this profile sheeting underneath, and we put some crack inducers over here. The purpose of crack inducers was to clearly define shear span, and shear span was from this point to the supports. So in this case, from this point to the end. And we carried out testing on 3 meter spans, and these were 3 testing as well. So this is shear span where this load is being applied. This is a normal testing procedure given in many design codes, Eurocode included. Then we have to plot Vt over B into dV is shear B, and dP is depth of the profile. And we have testing A and we have testing B. And from here we have a best fit line. The slope of this line is M, and this vertical component is K. So that's what we did for this testing. So we had in group A, we had 3 specimen, and group B, we had 3 specimen, and we plot them over here in this graph. And from there, we worked out this characteristic value of V over B dP as well. So these are all test parameters, which I tested at University of Leeds on Kingspan Multi-Deck 146. The trouble with this method is that every time we produce new sheeting, we will have to carry out this testing. So there's no other method. There's one method, partial shear method, but most of the time this MK test is used. But I think in modern design codes, this method will go away. And from here we get value of M as 140 and K as 0.05. And once we have these values, then what do? We put them into this Eurocode formula to work out longitudinal shear resistance, where we replace this M and replace this K. And then again, we work out this shear span, which is L over 4 in this case. And then we have a worked example on how do we use these MK values, but I will not go into details of this example. You will have slides, you can go through it yourself. We work out MPL-RD first, and then we work out vertical shear resistance as well, and then we work out longitudinal shear resistance. I will go to next question. Thank you.
Yeah. Next question is, how can we ensure adequate shear connection in composite beams?
Okay, excellent. Yes, this is very interesting. Again, very good question, in fact. We weld these shear studs through the decking to the top of the beam. And this process ensures that there is sufficient shear transfer between slab and the beam. Obviously, this can't be perfect. It can't be 100%. So minimum is 40%. But most of the time, in my view, it is probably 60, 65, 70%, not more than 70% in real life. And then stud, decking, and beam, they act as a single unit. Now, headed shear studs are most common ones. The typical diameter ranges from 19 to 22 millimeter, and typical length ranges from 100 to 200. We bring these shear studs on site, and then we have this weld collar, and then this is typical welding of these shear studs. Important thing to note here is that almost in all design codes, the diameter should not exceed 22 millimeter. especially for building type design codes. In Eurocode 4, which is code for steel concrete composite design, the diameter should not exceed 22 millimeter. I think in bridges they use 25 millimeter and 30 millimeter as well. But I'm not sure what design codes do they use. Here I would like to show you this quick video where you can see welding of this shear stud. This person is going to fall as well. So I think there was lots of wind over there. So this is how we weld these shear studs. Now, once we have welded these shear studs, then how do we check them? Now, this is absolutely crucial. You can see this person, this is holding a long steel rod. It has got hollow thing inside. So what he is doing is that he's putting this rod on shear studs and he is trying to bend it in both directions to see that if welding is fine or not. So this is very important. Otherwise, if shear stud is not welded properly, then quality assurance is not taken into account. So this is the way we check if shear stud is welded properly or not. I'm sure the place where you're working, they would use the same or similar thing. Now, other types of shear studs, they are not very common in buildings. We have these bar shear studs, and we have these channel shear studs as well. They are included in Eurocode 4. But in buildings, we don't use them. Now, other types of shear studs are this perforabond shear stud and this T-beam with dowel shear studs. These shear studs are there, but at the minute, we don't have design rules for these. So research is ongoing, and we will see if we have any design rules for them. And this has been taken from this R.P. Johnson's book. Professor R.P. Johnson, he is authority in steel concrete composite structures, and you would be surprised that he was my colleague at Warwick University. I have previously worked at Warwick University, and I used to get a lot of guidance from him. He has written a very interesting book, and it is a very good reference book for steel concrete composite structures. Now, these are some other types of shear connectors. And how do we ensure shear connection in composite beams? This is an example of solid slabs. So in solid slabs, we just pre-weld these shear studs, and then we pass reinforcement and we construct reinforced concrete slab. In case of secondary beams, when sheeting is perpendicular to beam axis, you can see here sheeting is perpendicular to beam axis. And this is the configuration where we have the secondary beam. So in secondary beam, sheeting is always perpendicular to the beam axis. And there's a different formula for shear stud for this case. In case of primary beams, sheeting, you can see that it is parallel to the longitudinal axis of the beam. And I think this figure, it gives really good sense of how it looks like. And again, in this case, we have this beam where not only sheeting is parallel, but it is supporting 2-point loads from secondary beam. So there are different formula for parallel sheeting. But in case of parallel sheeting, it's not necessary that you have shear connection, especially for internal beams. But for external, yes, obviously. But for internal beams, it's not necessary. But in case of secondary beams, 100% you will use shear connection. That brings me to question, what methods have you used or seen in practice to ensure reliable shear connection on site? I would be interested to see your views. Put them down in comments.
Okay.
Is it possible to stop my screen for a minute? I want to have some water. And Mike.
Yeah, sure. Yeah. Okay. Meanwhile, you can just respond to that question. Okay, I can see there are a number of points mentioned here. Meanwhile, when the presentation was going on, okay, one of the question which I can read out here is, if the end of the composite beams are of different spans, how to use torsional moments in irregular shaped structures? If possible, can you please elaborate? Okay. Okay, I mean, how to tackle the torsion? What measures you suggest? Okay. And please explain shear planes and fatigue. Okay. Yeah, I was just going through the few comments meanwhile.
Yes, yeah.
Yeah.
I think fatigue is issue in bridges. Fatigue is not taken into account in buildings. So there must be some provisions for fatigue.
Yes.
But I'm on top of my head. I don't have the exact formula.
Yeah.
And the other question was that in torsional.
Yeah, that was related to torsion.
Yeah.
If the end composite beams are of different spans, how to use torsional moments in irregular shaped structures?
I think for irregular shaped structures, then probably analysis should be carried out in a different way. And in design codes, I don't think we have any direct formula for composite structures.
Okay.
Yes. How do we determine shear connection?
Yeah. How
yes.
do we, yeah.
Excellent. So I will go through that one. So we ensure shear connection in beams by using these shear studs, and headed shear studs are the most common one. And these are typical properties of these studs: 450 Newton per millimeter square, elongation is 15%. They are very quick to weld, and they are strong in all directions. This is very important. So in case of load reversal or in case of other loading, the beauty of these studs, round headed shear studs, is that they are equally strong in all directions. So in buildings, almost certainly you will use headed shear studs. A small replica of beam tests, they are carried out to assess shear connector resistance to longitudinal shear. And these tests, they look like this. In design codes, we have push tests, which are for solid slabs. And in design codes, they say that they should at least have 6 millimeter slip. But surprisingly, no design codes, Americans included, will give you any push test for profile sheeting slabs. So they say that you should use the same configuration, but they don't specifically give you any guidelines for profile sheeting slabs. And in profile sheeting slabs, you will not have this 6 millimeter slip for ductile failure. Now, does this mean that in profile sheeting slabs, when we use shear studs, they are not ductile? The answer is no. Because when we use sheeting in a push test, it applies direct shear. But in case of beams, direct shear is not applied. When we apply loading, the load is vertical and then it is transferred in horizontal direction. And also flexure of beams, it will help as well. So mostly the failure is gradual. So in beam, you will have the slip, which is far more than 6 millimeter. But in testing for profile sheeting slabs, you will not have 6 millimeter. And to account for that, we did lots of testing. I did testing in horizontal direction as well. So this is testing in vertical direction. So for composite slabs with profile sheeting, there's no standard test in any design code. They've been trying to build some, but they couldn't get it. And we apply a reduction factor approach. So we work out the shear connected capacity for solid slabs, and then we apply that reduction factor. We first of all, we find out shear connected capacity for solid slabs, and then we work out reduction factor for profile sheeting slabs, and then we apply those reduction factors. Said this already, most design codes, they apply reduction factors to shear studs strength from solid slabs. This is the configuration for profile sheeting slabs. As you can see that in vertical direction, we have a beam. On two sides, we have profile sheeting slabs. And this configuration does not really work properly. So we thought to have a horizontal profile sheeting, and this was the configuration. So this is one of my PhD work, and I have one research paper. In fact, 4 or 5 research papers from this research, that we conducted this testing in horizontal direction and single-sided direction. So this is about 1.5 meter long slab in each direction, and we applied loading over here. And the purpose was to see that if we are getting this slip, which is not less than 6 millimeter. And these are some failure modes. So the failure happened by rotation of last stud. So this was loading direction, or in some cases, this stud was taken away from there. And the failure happened due to conical failure. So these concrete cones were formed around shear studs. Now remember this concept. I will ask you a question in a minute, that why these concrete cones they develop. And then we remove this slab from top of the profile sheeting. You can see that this is the first stud. You can see cones are quite a lot, and the bottom one, for not bottom, the last one, it is actually the stud is taken away from the, it's blown away from concrete, from a steel beam, and then last rib it rotated. Looking at here, what we do is that we say that the stud strength is divided by, there are 5 studs, 1, 2, 3, 4, 5, and we divide everything by 5. But looking at these cones, the cones do not match. So studs are the one which is near to loading, it is taking a lot of load. But again, this is the convention that we have been using in design codes, that we say that this is the stud strength. Now this is how we got shear stud strength, and you can see here that stud strength is about 70%. In design codes, what they do is that they carry out lots of testing, and they figure out what is shear stud strength, and they apply partial factors, and after applying partial factors, it comes out to be about 55 something. So that's how they do it in design codes. Surprisingly, here you can see that at 6 millimeter slip, the load is dropping. In Eurocode, it's a requirement that the studs should at least have 6 millimeter slip. But in whatever testing is done across the world, America, Australia, everywhere, this 6 millimeter is not obtained. And many researchers, they give this reason is that because this testing applies direct shear in real life. When we have a composite slab on top of the beam, flexure of beam itself, it helps. So the failure is gradual. In that case, the slip does not happen until probably 10, 15, 20 millimeter. So this requirement is met in case of beams. But these short tests, they don't fulfill this requirement, which means that we should have some different kind of testing for steel concrete composite beams with profile sheeting. Single stud per rib and double stud per rib. Single stud per rib, you can see that we have 70 kilonewton per stud, and here we have about 50, on average about 50 kilonewton. Why this capacity is less? If we have double studs, then certainly we should have more capacity. This is how it makes sense. But in case of double studs, the capacity per stud is reduced. What is the reason? What could be the reason? And from testing, what I have seen is that you saw these concrete cones earlier. Concrete cones, if you use double studs, then concrete cone is shared between those studs. The failure is mainly concrete in case of profile sheeting slabs. So when they are shared, then obviously the size of cone reduces, unless if you have a lots of gap between those studs, which is not possible because width of the top flange is limited. So that's the reason we have less load per stud in case of double studs and about 30% less. In case of single studs, we have more. Okay, now I have a question for you. Have you ever used push-out test data or relied on design codes to determine shear stud strength? I think another surprising thing, Bhavan, is that these design codes, they were developed for 50 to 80 millimeter deep decks. But nowadays, we have decks which are 100 and 150. Kingspan has 146. So when we use these design formula now, in American or Eurocode design codes, for deep deck, they give wrong values. So manufacturers, they have to provide these shear stud strength.
Okay. And always, this is one of the gray area I have seen that now what shall be the spacing of the shear studs, which is being identified in the drawings. So as you rightly said, it may be placed just maybe on a thumb rule basis or as an empirical formula basis. But as you rightly said, more details are required for this.
Definitely.
Some comment has come here. Yeah. No, we use the data provided by the manufacturer. I think that's a common practice in India, if I'm not wrong. Mostly, we are dependent upon the data which is provided by the manufacturer.
Okay. I think here in the UK as well, they use manufacturers' data. But in my view, there should always be some kind of design code or some guidelines which we can follow to independently verify. Because manufacturers, I have worked with manufacturers. What they do is that they just test one-off tests, and based on those tests, they have one value. So how about if that experimental value could be wrong? So I think it should be number of studies, it should be hundreds of testing before we can come up with any design formula, isn't it?
Yeah. So meanwhile, Alan is saying that he has used it, right?
Okay, excellent. Let's
Muhammad is interface share.
yeah.
Okay.
Let's
Shall we
move
go
to
to the
next
next
question.
point?
Yeah.
Sure. Next point is what is the effect of steel wire mesh position and the number of
Okay.
mesh layers on the strength of shear connectors?
I think did I share my screen or not? I think I didn't present share my screen. This is a very interesting question, and luckily I did some testing on that during my PhD. So that's why I'm able to answer that question. And otherwise I would have been in trouble. So this is the testing that I did as part of my PhD at University of Leeds. One is mesh on deck, directly on deck. Another is mesh, which is 30 millimeter from slab top. So here you can see that we use these small chairs over here so that meshing is raised. And this was the testing results. PTS1 is mesh on deck, PTS2 is mesh 30 millimeter from slab top. And interestingly, you can see that there isn't much difference. There isn't much quantifiable difference between mesh at top or mesh directly on steel deck. The only difference is that when mesh seems to be closer to head of shear stud, then it gives better shear stud resistance. But we cannot generalize the things because it will depend where you're positioning the mesh. And in my view, putting mesh on either top or 30 millimeter from top of the slab, it does not make much difference. And I think that this data is quite reliable. Now, how about number of layers? I think after we conducted this testing, Steel Construction Institute, in the UK, they have produced separate guidelines for number of mesh layers. And this is the testing for single stud and one mesh layer, and PTSNM is single stud, two mesh layers. So you can see that with two mesh layers, the stud capacity is a bit higher. But here in this testing, we applied 10% of the expected failure load as normal load as well. So in this case, not only we applied horizontal load, but we applied load at the top to mimic real life beam failure. But again, we were not able to get this 6 millimeter. The idea was that for ductile failure, we wanted to get 6 millimeter slip, but it did not happen. Although there is a 20% difference between these two, and I think Steel Construction Institute, they have produced the design guidelines as well that the capacity should be more for double layers. But again, this is my personal view that the results, the evidence is not conclusive. That could be experimental error, or that could be due to 10% applied load, or that could be any other reason. So there is no marked difference between these two. Now, in what situations do we use double layers if it is not helping increase stud strength? Again, in my perspective, where you're using the slab, concrete slab, which has got lots of depth, for example, if you're using 60 millimeter decking, and if you're using 250 millimeter concrete, then between 60 and the concrete depth is quite a lot. So we can have shrinkage cracks. To avoid those shrinkage cracks, we can use this double layer. But for increasing the stud strength, I don't think we should be using double layer. Again, this is another example for where we use double studs. And you can see that with double mesh layer, the capacity is higher. And this is real experimental data. And then I will directly go to next question without asking Bhavin, in the interest of time.
Yeah.
Failure modes.
Sure.
Yeah. So what type of failure modes we have in steel concrete composite beams? Now, first failure, here you can see in the first figure, it is stud failure. In the second one, where my supervisor, he's standing over there having a look at the concrete cones. So second is concrete. Let's have a look at first shear stud failure. Now here fracture of a stud happens, and this is how a stud will fail. And most of the time it happens in solid slabs. I have not seen this failure with profile sheeting slabs. And second is conical failure. In conical failure, concrete fails, forming cones. And here the stud is not failing. And this is one of the example where concrete is failing. And this is from my PhD research. And here you can see that concrete cones, this is finite element modeling as well. Concrete is cracking at the first rib and second rib, third rib, fourth rib, and at last rib, we don't have much cracking because the last rib is rotating. In profile sheeting slabs, most of the time, the failure will happen in concrete, and it will leave behind a cone. So if we have double studs, then cone will be shared. And as a result, the shear stud capacity will not be double unless if you increase the spacing of studs, which is not possible because the top flange is limited. Now this is very interesting. We have transverse spacing of 60 millimeter in case of this left figure. You can see that cones are shared here. This is indicating concrete cracking, concrete damage. Damage T means concrete damage. 1 indicates complete failure and 0 indicates no failure. And see that cones are connected. But if we increase transverse spacing to 400 millimeter, which is not possible in real life, obviously the width of top flange, it's 200 or 250 or maybe not more than 280. And 450 or 500 millimeter top flange is not possible, at least in buildings. Now here I increase the spacing between studs to about 400 millimeter. And you can observe that now individual cones are being observed. In that case, the shear strength, shear per stud, will be exactly equal to what you get in single stud. So it means that the dominant failure in this case is concrete failure, concrete shear cones. Shall we move to next question, Bhavin?
Yeah, sure, please.
So next question is, yeah, please ask.
Yeah, how is the design resistance of headed stud shear connectors calculated?
Okay. How do we work out design shear studs? So first we work out design shear stud as per Euro Code 4, and most design codes, they have same approach. Understand that once we have these failure modes, we can relate these failure modes to design formula. Here, first formula, PRD, which is for mode 1, it means concrete steel is failing. Here, FU is ultimate strength of shear stud, and D is diameter of shear stud. It means that it is just valid for headed round shear studs, not other shear studs. So steel is failing in mode 1. In mode 2, all dimensions you will see, FCK is related to concrete, ECM is related to concrete, and this is a concrete failure. So in solid slabs, steel can fail and concrete can fail. And this is the headed shear connector and profile sheeting. And this is the failure of vertical profile sheeting, and you can see this concrete failure. But previously I showed you the concrete failure cone, so that shows it better. Now, how about how to work out headed shear connector design resistance in profile sheeting slab? Now, behavior is very complex here. We always use a reduction factor. And first we get the design shear resistance for solid slab. Then we multiply it with a reduction factor. So for sheeting where ribs are parallel, the reduction factor is KL. For sheeting where ribs are transverse, the reduction factor is KT. And this approach is used in American codes, and I'm sure in Indian codes as well. So we work out the design resistance of solid slab, and then we work out these reduction factors. So parallel ribs means it is primary beams, transverse means that it is secondary beam. Now this is the formula for parallel, and we have this KL 0.6 B naught. HP is the height of the profile, HC is height of shear connector, and from here we find out reduction factor. And secondly, we have reduction factor for transverse sheeting. Here sheeting is perpendicular to the axis of the beam, which is secondary beam configuration, and here we have a reduction factor again. And once we have found out these two reduction factors, then these reduction factors, they should satisfy this KT max requirement as well. So if the thickness is less than 1, so it should not exceed 0.85, and these are other requirements in Eurocode. Now, once we have these two failure modes, these two design shear resistances, which are steel and concrete, then we multiply them with their respective reduction factor, and then we choose the one where we have less concrete, where we have less shear stud resistance. So for example, if it is coming out to be 70 kilonewton in case of steel stud failure, and if it is coming out to be 50 kilonewton in case of concrete failure, then you choose the lesser of these two. It means the capacity will be 50 kilonewton. In that way, we work out shear stud resistance. And then I would like to move to the next question, Bhavin.
Yeah, sure. So the next question is, what are the key steps involved in designing steel concrete composite beams?
Okay. Again, there are so many steps, but I will give a high level summary of what needs to be done. And I have a full tutorial on this topic on my YouTube, which is one of the famous one as well. So design for steel composite beam with profile sheeting. First, you have to select sheeting, or you have to design a composite slab. Depends on you, based on manufacturer's guidelines, or you can work out the manual calculations yourself as well. And then we have to determine loads. Then we have construction stage. Then we have composite stage. Now, what is the difference between construction and composite? The key difference is that at construction stage, we have to ensure that sheeting is sufficient to take loading from people, workmen, and wet concrete. So wet concrete is considered as a live load. In composite stage, same concrete is considered as dead load. So this is the difference. So when you apply these 4 steps, then you can. This is construction stage, where you can see that the decking has to support load of these people, this machinery, and also concrete. And this is composite stage when concrete has hardened. Now, what permanent actions and variable actions? I'm sure these terms might be new to you, but this is another fancy way of Europeans to make things complicated because we want to impress people. Permanent actions means dead loads. Variable actions means live loads. So I will call it, for the simplicity, dead and live rather than permanent and variable. All right. So at construction stage, we have deck and mesh and steel beam. These are permanent loads. Variable load is wet concrete. It is live load. It is not considered dead because we are pouring concrete, and construction loading of 0.75 kilonewton per meter square. So when you are checking sheeting, you have to work out loading based on this, and then you work out its moment, and then you compare that moment with the moment capacity, which I showed you earlier for multi-deck 146 millimeter decking, which was from manufacturer, or you work it out yourself using elastic and effective properties. In composite stage, you have deck and mesh, steel beam. Dry concrete now is dead load, finishes, services, and ponding effect. Ponding is that if you have deflection of sheeting at wet stage, it will develop more height in the middle as compared to the ends. So we have to avoid that ponding. And imposed loads means occupancy loads and any movable partitions. These are live loads. So once loading is done, then the complete procedure is here. So if you note this down, bit.ly/CB means composite beam, dash LEC means lecture, bit.ly/CB means composite beam, dash EX means example. So these are two videos that you can follow to design composite beams for profile sheeting. And you will have links to these. I have passed on the presentation to Bhavinsha and he will send it to you. Or you can note it down now, it's up to you. Shall we move to next question, Bhavin?
Yeah, so I think probably we can take up last question now.
Yes.
Which design software and tools are used for designing composite structures?
Excellent. Is my screen shared? My screen is shared, isn't it?
Yeah, you can go ahead, please.
Okay. I think, in my view, for composite structures, there isn't any proper design software because the sheetings, they keep changing. So almost certainly you will have to rely on manufacturer's guidelines, or you have to do some calculations yourself. And I have used this S-frame, which provides composite beam design. I've not used other software for composite. So here you can guide me if they have these provisions or not. I've taken the information from their website, but I haven't specifically used them. So use this information with caveat, right? And design tools, I find these BCSA tools, British tools for composite beam checks, very useful. And Steel Construction Institute guides, Excel-based sheets, so which can incorporate Indian codes. Tekla Designer, it has got some thing as well. And for S-frame, I found this video very useful. So I have this link. It is from Matthew Seaver, who is the technical director of S-frame. It's a Canadian company, and they have software. This guy, he met me in London as well 5 years ago. So you can click on this link and have a look at this YouTube tutorial. And also this tool is very useful. If you go to my YouTube, you will find this tool as well. BCCA tool for composite beam design. And they're complete software and tools used in the UK. This is the link. You can scan this barcode or go to this link for designing them. And then I have used these resources. You can have a look at these resources. Steel Construction Institute guides, I've used these guides as well. And this is the book which I will recommend, by R.P. Johnson. R.P. Johnson, he was my colleague at University of Warwick. I worked there briefly between 2010 and 2013. And he was involved in writing Eurocode 4 as well. So this book is really very useful. Use this as a reference. It's got generalized concepts as well. We have another book, and I saw some books about joints of composite structures. So you can use this book for composite structures. If you're looking for examples, then this book is useful as well. And you might like my steel design series to Eurocode. So this is a link to Eurocode series, or type in Dr. Jawed Qureshi steel design. And these days, this has become so popular that our dean, he typed in ChatGPT that who is the leading academic in steel design. So he got my videos there in ChatGPT. You can scan this barcode to go to my YouTube, or simply type in youtube.com/@Dr. J Qureshi. And if you like this presentation, you can see me there. And on LinkedIn, where I found my friend where I found my friend Bhavin Shah, and this is how we got connected. This is the link to my LinkedIn, linkedin.com/Dr. Jawed Qureshi, or you can scan this barcode as well, and you will have a copy of slides. Take your time, get connected with me, and we can share information. And I want to learn from you as well.
Yeah.
And with this, I will end my presentation. Thanks a lot for bearing with me. It was a long session. And I will stop sharing my screen. This is University of East London, where my office is. This is London City Airport on the left side. You can see runway. And my office is around over here, where my arrow is. And there's a Docklands Light Railway, which is a driverless train over here. The station is inside the university. So if you ever come to London, by all means, come and visit me. And I'm happy to take any final questions or final thoughts.
Yeah. Okay. Great. Excellent presentation. Yeah. And yeah, as we discussed in the beginning, also it's a very wide subject, right? And a lot of details are required. Yeah. Okay.
I think we will have next session on FRP structures, so that would be very interesting.
Yes. Okay. Great. Kumar is saying that is the deck sheet takes the human load while concreting, and second, is the needle vibrator used for deck sheet concreting?
I haven't seen needle vibrator for deck sheeting, but it might be used. I haven't seen it, the needle one. And human loading while concreting, yes, because we take this workman load 0.75 kilonewton meter as live load. Yes, it does.
Yes. Okay. KS Vivek is giving reference to Indian standard, table 9, 10, 11 of IS code. It is providing static strength, reduction factor, and fatigue strength for stud shear connections. Yeah.
Okay.
Okay.
This is something I will look into it, because thank you very much.
Yeah.
As
Yeah.
well.
Yes, great. Great.
Also,
Yeah.
I think I really enjoyed this session. You can type in any future topics that you want us to cover, and we want to make things a bit very interesting as well, and uh, we want to take things at a higher level, at conceptual level, rather than simple calculations. And I'm sure you would have learned quite useful things today in terms of how we integrate research uh, into not only teaching but in practice as well, and why research is really important in this area.
Yes. Yes. Okay. Omar is saying one last question. Connection beams and columns in composite structures. Where do you take moment from, in X direction or Y direction?
I think it will depend on configuration, and if you have a secondary beam, I mean, certainly in the direction of longitudinal axis you will take the moment. Yes, it will depend on configuration.
Yeah. Okay. Dr. Subramanian Narayan sir saying thank you for the
Thank you.
elaborate, Professor. Yeah.
Thank you so much. I enjoy your newsletters, Dr. Subramaniam,
Yeah.
and you are one of the academic which inspire every generation. Thanks for attending the session.
Yeah. Yes. Yes. And he's really actively participating in numbers of sessions.
And my knowledge is limited as compared to yours as well.
Okay. That Qureshi is saying that in areas like India, where propping and labor is cheap relatively, do you feel we have to compulsory go for propped composite structures?
I think so, because with the prop one, you can increase the spanning capability. Yes, why not?
Hmm. Okay. Thank you.
Thank you. Muhammad Omar is quite regular visitor of my LinkedIn. I see his comments quite a lot. Yeah.
Okay. Alan is saying that thank you for this presentation. I appreciate the research data. Please add me to
Thank
your
you.
slide circulation. Yeah, sure. You will receive that. Yeah.
Thanks a lot.
Okay. First problem. Yeah. Okay. So let us stop at this point, and of course we'll come up with more and more interesting discussions. So you can still keep in contact with us, and then please keep on sharing your additional comments, feedbacks for this topic as well as for the other topics, right? And then accordingly we will decide future sessions. Yeah. So with this, we are signing off now. Okay, one more comment, last comment we can say. Okay. Thank you,
Sure.
doctor, from South Africa. So
From South Africa. I'm actually going to South Africa in September. So if you're in Cape Town, probably we can meet up.
great.
1st to 3rd September.
Great. Okay. Santosh Kumar says thanks a lot. Okay. Saeed Ali says thank you so much, sir. Yeah. Okay. The answer is sure. Yeah.
I think
Okay.
I
So
think I should be
with this,
I
yeah,
should
yeah,
be
please.
I should be thankful to Bhavin Shah for inviting me for this session. And as always, I enjoy your company and your audience. They are
Yeah,
absolutely wonderful as well. And
yeah,
we will meet up next time very soon. Thank you.
yeah, sure. Yeah, sure. Most welcome. The whole credit goes to the audience because they give very interesting discussion points in advance, and during live session also they are interacting, right? And that
Yeah.
gives that's the real strength of the session, right? Yeah. Okay, okay. So we are signing off now. Goodbye.
Thank you. Thank you so much.
Most welcome. That's right.
Have a nice
Bye.
evening.